All right, Ninja Nerds, in this video we're going to talk about enzyme kinetics. But enzyme kinetics, what is it basically? Well, kinetics is referring to basically the rate of a reaction or the speed of a reaction. So it's basically just turning the rate or the speed of a reaction with respect to an enzyme. But it's kind of an umbrella term for a lot of different concepts that we're going to cover within this video. The first thing we're going to do, because we're going to talk about a lot of stuff, we're going to talk about the Michaelis-Menten Equation, we're going to talk about its graph, the Lineweaver-Burke plot, competitive, non-competitive, uncompetitive, and even suicide inhibition. But before we do any of that, we have to develop a clear concept of this Michaelis-Menten equation. So what we're going to do in this video is we're going to start with basically this concept, this reaction, and derive the Michaelis-Menten equation. So let's go ahead and dive right in. All right, so the first thing, so I wrote here Michaelis-Menten equation. We're going to derive it. I'm going to show you how we get to that point. But we need to understand this general reaction right here. So what does E stand for? It stands for the enzyme. So an enzyme is reacting with the substrate. And when it reacts with the substrate through like an induced fit or a lock and key model, it'll form an enzyme-substrate complex. And then what happens is that enzyme-substrate complex will dissociate into enzyme and product. So what we can say is the constant, or the rate at which the enzyme and the substrate is turning into enzyme substrate, we can denote this arrow right here, this one going towards enzyme substrate, as K1, right? Then we can actually denote this enzyme substrate dissociating back into the enzyme and the substrate as K-1, okay? And then we can say that the enzyme substrate, when it completely dissociates into enzyme and product, that is K2. And then technically there is a reaction, there is a reversible step here with enzyme and product going back to enzyme substrate, but it's so small that at, when time is equal to 0, that the K-2 is so small that we can just consider it to be negligible. So this is just a unidirectional reaction. Okay, now that we've done this, we have to make a certain assumption. What's that assumption called? They call it the steady state assumption. And basically what the steady state assumption is that your enzyme substrate formation is equal to the rate of enzyme substrate dissociation. So for example, if I were to kind of make like a graph here, and let's say that I have enzyme plus my substrate, what's going to happen is as this reacts, its concentration is going to decrease over time. But then what happens is my enzyme and product is going to be increasing over time as the enzyme substrate decreases. But there's this point where the enzyme substrate is constant throughout that entire process. That's what our steady state assumption is saying. So again, what can we say? The steady state assumption is equal to the rate of formation of the enzyme substrate and the rate of dissociation. So let's go ahead and write that out then. So if we say the steady state assumption is the rate, I'm going to put F for formation, is equal to the rate of D for dissociation. Well, which one of these reactions, if we're looking at these Ks, which one is actually going to form the enzyme substrate? Well, if I look here, the only arrow going to the enzyme substrate is this K1, where my K1 is telling me the constant, right, the rate at which this enzyme and the substrate is turning into enzyme substrate. So that's one reaction. So what's the rate for that? Well, it's K times the concentration of my reactants. And we're assuming it's like first order here. So again, this would be K1 for the rate times enzyme times substrate concentration. That's the rate of its formation. Is there any other reaction? Well, there would have been K-2, but again, at time equals 0, we're assuming that that K-2 is so small that it's negligible. So the rate of dissociation, which one is showing the enzyme substrate complex breaking down? Well, this one is, and so is this one. With K-1, it's going back to enzyme and substrate. With K2, it's going to enzyme and product. So what can we do here? K-1 times enzyme substrate, because he's acting as the reactant and he's dissociating into enzyme and substrate. What else? K2, so we can add that, because K2 is showing the enzyme substrate breaking down into the enzyme and product. So we say K2 is going to be times enzyme substrate concentration. Now what? We've formed our steady state assumption. Now we need to do something else. There's always, when we have enzyme, right? So if I say that there's a total amount of enzyme, what is the total amount of enzyme? The total amount of enzyme is basically the amount of enzyme that's bound to the substrate as well as the free enzyme. So when I take this into consideration, the E total is the enzyme substrate plus what? The free enzyme. So the enzyme total is equal to the enzyme substrate plus the enzyme, which is free enzyme. Now, what I'm going to do here is I'm going to make an assumption here. And I'm going to say what I really need to plug into this equation right here for that E right there is I want to plug in whatever E equals with respect to this equation. So what does E equal in this equation? E equals, if I subtract over the enzyme substrate, it's equal to enzyme total minus enzyme substrate complex. Right? And I shouldn't have a lowercase, I should have an uppercase here. Enzyme substrate. Now what am I going to do? I'm going to take for here at E, and I'm going to plug this right into the E. So let's go ahead and do that real quick. So K1, right, and I'm going to put a parentheses here, is E is equal to enzyme total minus enzyme substrate. And then what else? Let me put another parentheses here because that'll come around that E. And let's put the substrate concentration out here. That's equal to all of this. So let's just rewrite this. K-1 times enzyme substrate plus K2 times enzyme substrate. Okay. Now that we've done that, let's go ahead and follow our mathematical properties, and we can do two things. One thing is I can distribute this K1 into this whole concept, into this whole, the parentheses in here, so I can distribute the K1 into each one. And look what else I can do. I can distribute the substrate into each one. Another thing I can do, if you look here, I have K-1 enzyme substrate plus K2 enzyme substrate. Enzyme substrate is a common factor between these two. So I can pull out the enzyme substrate out of this, out of both of them. So what is that going to look like after I kind of simplify this? So I'm going to distribute these two guys in first. So we got K1 times enzyme total times substrate's going to get distributed in there also. Then I'm going to distribute this K1 into this and this substrate into this, right? So I got K1 times enzyme substrate times substrate concentration. So again, I'm going in here and then in there, and then I'm taking this guy in here and then in there. And this is what I'm getting out of that. And then what does that equal? That equals, and remember I said I was going to pull an enzyme substrate out of both of these guys? Well, enzyme substrate is equal to, parentheses, K-1 plus K2. Okay, now look what I can do. I have a K1 here which is similar across both of these equations. And the reason why I want to factor this one out is because there's another equation that I'm going to use here. There's an equation that says Km, which is your Michaelis constant, is equal to your K-1 plus K2 over K1. So we can say that this is the rate of dissociation over the rate of formation is equal to the Michaelis constant. Well, I already have this part. I got to get K1 over here. All right, so let me get rid of this equal sign here, guys. That doesn't belong there. Let me actually fix this up a little bit, make it look a little nicer. Okay, so now that we have this Km here, and we got this K-1 plus K2 over K1, now what can I do? I can factor out this K1. Let me factor that K1 out now. So if I factor out K1, what do I have now? I'm going to have enzyme total times substrate, and I'll put a parentheses there for this guys right there. And then what? Minus, what am I going to have over here? Enzyme substrate concentration, all equaling enzyme substrate times K-1 plus K2. Okay, now what do I do here? Now I can go ahead and divide this K1 over here. So let me do that. Let me divide my K1 over. So I'm going to divide my K1, and then what do we get? Well, this guy cancels this guy out, and this whole term here turns into Km, right? Because that's what Km equals to. The Michaelis constant is K-1 plus K2 over K1. So now let me simplify this. So I'm going to have enzyme total times substrate minus enzyme substrate times substrate. Then what am I going to do? Make it equal to enzyme substrate, and all of this is Km. Now, I want to add over this. I want to add over my enzyme substrate plus the substrate, because I want to get my enzyme total by itself, and I'll show you why in a second. So let me go ahead and do that. Let me add over my enzyme substrate times the substrate concentration onto both sides. So what I get over here, let's see what we get out of this. We're going to get enzyme total times substrate concentration equals enzyme substrate times Km, right, plus enzyme substrate times substrate concentration. Let me fix that up and make that look a little nicer, guys. So again, enzyme substrate, substrate concentration. Now what can I do? Now if you notice, look what I have here. I have an enzyme substrate that I can factor out of both of these guys. Let me go ahead and do that now. So I'm going to factor that out. So if I factor that enzyme substrate out of both of these guys, what do I get? Enzyme substrate, parentheses. I'm going to pull this guy and that guy out, so it's going to be Km plus substrate concentration, all equaling enzyme total times substrate concentration. All right, so now it's looking pretty good here. So now what I want to do is I want to get my enzyme substrate by itself. Why? There's another equation we're going to use here in a second, and it's V0, which is the initial velocity, is equal to your K2, the rate of dissociation into enzyme and product, times the enzyme substrate concentration. This velocity is dependent upon the rate at which the enzyme substrate dissociates into enzyme and product. In other words, I got to get this enzyme substrate by itself so that I can plug in what? What is enzyme substrate equal to in this equation? It's equal to V0 over K2. So I need to plug this term into my Michaelis-Menten equation because this is too hard of a concept to be able to focus on. I need to use other ways to be able to get this enzyme substrate equal to this concept here. So let's go ahead and do that now. So if I look, how do I get enzyme substrate by itself? Divide over by Km plus substrate concentration. This cancels out, and I'm going to divide over here by Km plus substrate concentration. And what do we get out of this? Okay, let's write this all out now. Enzyme substrate concentration is equal to what? This cancels out, and I'm left with enzyme total times substrate concentration all over Km plus substrate concentration. Now, what did I say? Remember I told you that the enzyme substrate is equal to what? The V0 over K2. Well, I'm going to take and plug that in now because now's the time that I can apply that concept now. So let me go ahead and do that. So let's go ahead and do this over here now. Let's come up. Okay, now, if I plug in V0 over K2, that's equal to what? Enzyme total times substrate concentration over Km plus substrate concentration. Okay, now what do I do to get V0 by itself? I multiply by, I'll take the inverse or the reciprocal of K2. What's the reciprocal of K2? Well, then I just do K2 over 1, cancels that out, and what do I have over here? I'll have K2 over here. So I'm just going to I'll rewrite this now. K2 over 1, what do you get? V0 is equal to K2 times enzyme total times substrate concentration over Km plus substrate concentration. Here's where we make another assumption. And our last assumption. At this point in the reaction of where your enzyme is reacting with your substrate, making the enzyme substrate complex and getting converted into enzyme and product, we're assuming that there is a point called Vmax. And Vmax is the point at which all of your enzymes, so remember, what was our enzyme? Our enzyme is equal to our enzyme total minus the enzyme substrate. Or we can say the total amount of enzyme is equal to enzyme substrate plus the enzyme. Now, there is a certain point in time when we reach maximum velocity, Vmax, in which all of the enzyme substrate is completely formed and there's no free enzyme left. In other words, you know how we had enzyme plus substrate to make enzyme substrate complex? There's no more enzyme left over here to react with the substrate to make enzyme substrate. So what do I have left then at Vmax? Enzyme substrate. But what's my enzyme substrate equal to when I'm at Vmax? E total. Well, what was V0 equal to? K2 times enzyme substrate. That was your V0, right? But now our maximum velocity is equal to K2. And now again, there's no more free enzyme left. We're at the maximum velocity. What does that mean? All the enzyme is completely saturated with substrate. There's no more substrate, there's no more enzyme available to add substrate. No free enzyme. So that means now enzyme substrate equals enzyme total. So I can actually substitute an enzyme substrate with enzyme total. Where do we see that in this equation? Right there. So now what can I do? I can say V0 is equal to Vmax times substrate concentration all over Km plus substrate concentration. And what do we have here? This right here, my friends, is the Michaelis-Menten equation. That's a big mofo to go through and derive, right? But again, what's the whole concept of this? We can get from this general reaction, we can derive an equation that's going to help us to understand a plethora amount of concepts related to enzyme kinetics. This formula is essential to understanding these enzyme kinetics. But I have to do one more thing before we finish up and start going into these concepts. I need to understand the concept of Km more specifically than just this. So now I need to apply this concept with respect to the Michaelis-Menten equation and Km. Let me do that quick now. All right, so if you remember, when we talked about Vmax, right? What we can do is we can make this assumption. So what I'm going to say is that if I say that V0 is actually the point at which Vmax is halved. So in other words, I'm going to rewrite V0 as Vmax over 2. All right? And then I'm going to make it equal to this equation. So V0 is equal to Vmax over 2. All right? So if I do that, so V0 is equal to Vmax over 2. And now what I'm going to do is I'm going to plug this Vmax over 2 into this equation over here. So let's go ahead and do that. So if I come over here, I'm going to say now, actually I can just start it right here. I can say now that Vmax over 2, which is again, half Vmax is equal to that V0 point there. I'm going to make this equal to Vmax times the substrate concentration over Km plus the substrate concentration. And then what I'm going to go ahead and do is I'm going to try to solve for Km, because I want to understand something about the Michaelis constant here, more than just that equation of it's equal to the K-1 plus K2 over K1. So let's go ahead and do this. So what I'm going to do is I'm going to take the inverse of Vmax over 2 here, right? Or I could just, let me just actually cross multiply. So I'm going to cross multiply here. So I'm going to get 2 Vmax times substrate concentration equals Vmax times Km plus substrate concentration here, right? Because all I did was just cross multiply. Then what I'm going to do is I'm going to divide over by Vmax. And when I divide over by Vmax, what do I get? If I have 2 substrate concentration here, right, because the Vmax cancels out, it's equal to Km plus substrate concentration. And I'm going to get Km by itself. How? I'm going to subtract over the substrate concentration. And what does that give me? Well, 2 substrate concentration minus 1 substrate concentration is equal to 1 substrate concentration. So what's the overall thing left over? Km is equal to the substrate concentration. When? When you're at half the maximum velocity. So when it's at half Vmax. This is another critical concept that we are going to need here to understand a little bit more about enzyme kinetics. One more thing before we finish this video and start going into a lot of the enzyme inhibition here, is I need to explain one more thing with respect to Km. Km in the simplest terms, because this is not necessarily the most true concept, but it's going to help us to understand a little bit more about affinity, even though this isn't necessarily completely true, but it's going to help us. When we talk about Km, Km tells us the substrate concentration at half Vmax. It also kind of helps us to understand the affinity of an enzyme, that the affinity that the enzyme has for a substrate. So if we have a low Km, a decreasing Km tells us that that enzyme will have high substrate affinity. So we can say that a low Km equals high substrate affinity. Okay, then we can say the inverse. If Km is really high, then we can say that it has a low substrate affinity. So this one had a high substrate affinity. This one will have a low substrate affinity. To explain it in even a better way here is it can tell us how much substrate the enzyme can take on. So with an enzyme with a low Km, it's going to have a high substrate affinity, so it's not going to be able to take on large amounts of substrate. With an enzyme that has a high Km, it has a low substrate affinity, so it's going to be able to take on larger amounts of substrate. This is a perfect physiological example here of two isozymes, and I'm just going to mention them just for the heck of it here. There is two enzymes that perform the same function in the body and our cells. This one right here with a low Km, we can find this in our muscle cells. This enzyme is called hexokinase. And all it does is it puts a phosphate on the 6th carbon of glucose. There's another one that does the same function, but it has a high Km because it takes on more substrate, so it has less substrate affinity. This enzyme is called gluco. Let me fix that, sorry guys. This is called glucokinase. And this is found in the liver. So hexokinase is found in the muscles, glucokinase is found in the liver, and they're form the same function. They're called isozymes, so they're similar enzymes with similar functions. The only difference is the amount of substrate that they can take on and their affinity for the substrate. So this formula is super critical for our understanding of enzyme kinetics. This one right here, as well as this one right here. Okay? So out of everything that we talked about here, the big concepts that you guys should grasp out of everything is the Michaelis-Menten equation, understanding how we derived it from this whole, what part here, this is another concept that we should really make important here, is from this steady state assumption, which is that the rate of formation is equal to the rate of dissociation, right? Again, these are another two big concepts to get out of all of this. And then to understand how we get the Michaelis-Menten equation and the relationship of the Michaelis-Menten equation with Km. Now that we've done that, guys, now we can go ahead and start talking about enzyme inhibition. All right, guys, so I'll see you guys in the next video where we'll talk a little bit more about enzyme inhibition and Michaelis-Menten graphs and Lineweaver-Burke plots.